In this video we're going to look at the trends in the Group 7 chemistry. First thing you'll notice in your booklet is this diagram, this picture, where we've got our different halogens. Fluorine is barely perceptible, but it's a yellow gas. Chlorine's a green gas. Bromine is a red liquid. It's got this kind of orangey hue to it. And then iodine is kind of this dark grey solid, sometimes quoted as being black. And here the physical properties are summarized in this table. Again, showing that showing what the melting point is and the boiling point. Also here on the right hand column we've got the total number of electrons total number of electrons in each atom. And this is really important because this helps us to deduce why the melting points and the boiling points are such. Okay, you do need to know these physical states at room temperature. Okay, now the big thing, one of the big things you must get your head around straight away is that the halogen molecules, when we say halogen, we mean F2, Cl2, Br2, I2. When we talk about halides, we're talking about F minus, Cl minus, Br minus, I minus. Okay, we don't really discuss the chemistry of astatine too often. It's radioactive and it's very short-lived. So very, very important that you understand the difference between a halogen molecule and a halide ion. Okay, so the trend in the melting points and boiling points. So the first thing you can see looking at this diagram of the atomic radii is that the atomic radius is getting larger as you go down the group, and you know that from your trends, the trends that you've studied in periodicity. And here we've got the diagram of the molecules. So the halogens exist as diatomic molecules, so that means we've got 2 of each atom per molecule. And so we can see that the atomic radius increases of each atom here. Okay. This is really really important because this dictates some of the redox chemistry that we'll come on to at a later date. So the atomic radius increases down the group, so the outermost electrons are further away from the nucleus. Okay, this means that they're going to be less attracted, so the outer electrons in iodine are less strongly attracted to the nucleus than the outer electrons in fluorine are. Okay. There's also more shells, so there's more shielding in an atom of iodine compared to the others. Okay. The ionic radius also increases down the group, and again that's more important when we're considering some of the reactions. The ionic radius is slightly larger than this corresponding atomic radius, and so the reason for this is that there's the extra electron gained increases the repulsion in the orbitals very slightly, but there it is a measurable effect that we see. Okay, so just going to skip electronegativity for the moment. Melting points and boiling points. So the diagram here shows us that we've got molecules fluorine, chlorine, bromine, iodine, and these dotted lines represent the attractive forces between molecules, or the intermolecular forces. Now, these molecules, the halogens, are symmetrical. They have the same electronegativity. They are 2 atoms of the same elements. Therefore, they are non-polar. Because they are non-polar, the only attraction we have between the corresponding molecules is van der Waals forces. So this means that the strength of the van der Waals force between neighbouring molecules is dictated by the number of electrons in that molecule. So fluorine, fluorine molecule, each atom's got 9 electrons, so it's got 18 electrons there. So it's quite small. Also means it's not going to be readily polarized because it's such a small molecule. So they're going to have weak forces, and that's why we have such a low melting point and boiling point. Whereas for an element such as iodine, iodine has, I can't remember, it's between 50 and 60 electrons per atom. So you've got somewhere in the region of about 120 electrons here. These electrons are occupying a larger volume of space, so therefore there's a chance for a bigger amount of polarization, and so therefore we're going to have a larger temporary dipole across a molecule of iodine, which will induce a large temporary dipole in a neighbouring molecule. So then you have stronger van der Waals forces between these molecules. Okay. So this means that we have a high melting point for iodine. This is the only solid we have at room temperature out of the 4 we study, because of the strong forces of attraction between the molecules require more energy to overcome. Okay. So remember, these are all dictated by the van der Waals forces, and that depends on the number of electrons. Okay, so now we're going to look at electronegativity. First of all, just a reminder what electronegativity is. It's the measure of attraction by a bonded atom for the shared pair of electrons in a covalent bond, i.e. it is the attraction between the nucleus of an atom and the outer shell of electrons. Fluorine, as you know, is the most electronegative element because it's the smallest element which can form a covalent bond to another atom, which is on the right hand side of the periodic table. Okay, so we're going to look at hydrogen chloride and hydrogen iodide. So if we just look at this this short picture here. Okay, we've got a hydrogen chloride molecule and a hydrogen iodide molecule. Hydrogen chloride is a much smaller atom because it's got 2 shells worth of electrons fewer than iodine does. So the shared pair of electrons will be here, and the nucleus of the chlorine here. So chlorine has got is more electronegative because of the shorter distance, and because there's less shielding in this atom, then it's going to have a greater attraction for the electrons which would appear here. Iodine, on the other hand, is a much larger atom, so it's got more shells of electrons, and the bonded pair of electrons are further away from the nucleus. They are more shielded from the nucleus, and therefore they're going to be less attracted to the nucleus. And so iodine is not a very electronegative element here at all. So fluorine is very electronegative, chlorine quite a bit, bromine less so, iodine is really not that very electronegative at all. Okay, so that's all I wanted to say about the trends in the group 7. Thank you for listening.